Hello class, welcome to Chapter 1. In this chapter we'll mainly focus on measurements. Now before we begin, please make sure you read the following sections either before or after this screencast. This statement is important to remember that no measurement is exact, no matter how precise the instrument is. The image below shows that you cannot measure better than 1 millimeter. With the ruler. There will always be some uncertainty. Here are a couple of definitions you should know. Estimated uncertainty is written with a plus or minus sign because a ruler cannot measure better than 1 millimeter. The estimated uncertainty would be plus or minus 1 millimeter. Now, to keep the units the same with 8.8 centimeters, we would write the estimated uncertainty to be 8.8 plus or minus 0.1 centimeters. Now, percent uncertainty is taking the ratio between 0.1 and 8.8 and multiplying that by 100% to get an answer of about 1%. Here's a conceptual example. A friend asked to borrow your precious diamond for a day to show her family. You're a bit worried, so you carefully have your diamond weighed on a scale which reads 8.17 grams. The scale's accuracy is claimed to be plus or minus 0.05 grams. The next day you weigh the return diamond and getting 8.09 grams. Is this your diamond? The actual mass lies between 8.12 and 8.22 grams. The actual mass of the return diamond lies between 8.04 and 8.14 grams. So since these two ranges overlap, you do not have a strong reason to doubt that the return diamond is yours. The next topic that's important to understand is significant figures. Now you may have already been exposed to significant figures if you've taken chemistry, so this may be a review for some of you. Significant figures is a reliable number of digits. In the first example here, there are 4 reliable digits, so significant figure would be 4. In the next example, the significant figure is 2 because the zeros don't count as reliable digits if the number is less than 1. The last example is a bit tricky because it could have either 1 or 2 significant figures. If we were to rewrite the number as 80.0, then the significant figure would be 3. Knowing the value of significant figure is useful for knowing how many numbers to write down as your answer or where you should round. When multiplying two numbers, that answer should contain the same number of significant figures as the least significant figures in your calculation. So for example, we have 11.3 centimeters, which has 3 significant figures, whereas 6.8 only has 2 significant figures. So therefore our answer should only contain 2 significant figures. If you were to type out this calculation in your calculator, you would get 76.84 centimeters. Now knowing the rule of significant figures tells us that we should round our answer to 77 centimeters because only 2 digits are significant. The same rule applies for adding and subtracting. Now when you're using your calculator, the correct number of significant figure is not always shown. Sometimes your calculator gives you too many digits or not enough. The top example shows 2.0 divided by 3.0. The least amount of significant figures in this calculation is 2. So our answer should only have 2 significant figures. Thus, the correct rounding would be 0.67 as our final answer. Below is another example of multiplying 2.5 times 3.2. Again, the least significant figure in this calculation is 2. So our answer needs to have only 2 significant figures. Thus, the correct way to write this answer would be 8.0. Here's a conceptual example. Using a protractor, you measure an angle to be 30 degrees. How many significant figures should you quote the measurement, then use a calculator to find cosine of the measured angle? Now looking at the protractor here, the precision is only 1 degree. So you can quote 2 significant figures, not 30.0, which is 3 significant figures, and that's because the precision is not 0.1. You cannot measure 0.1 on this protractor. So the correct rounding for cosine of 30 would be 8.87, which is 2 significant figures. The next topic we need to cover are quantities and units. In physics, we use several different letters, even Greek letters, to represent variables and units. In this course, we'll use the SI standard unit system for most problems. A few SI standard units is meter for length, seconds for time, and kilograms for mass. The standard notes to the side here are just fun facts on how scientists define a meter, seconds, or kilogram. Now don't worry, I won't test you on these fun facts here. Here is a full table of prefixes for units, along with the letters and with the power of 10 value for writing your answer in scientific notation. In this course, we may go as high as giga and as low as pico. But most commonly, we'll use milli, centi, and kilo. And in later chapters, during the second semester, we'll use micro quite frequently. Most importantly, in this course, you need to be comfortable with converting units. Most conversions will be to the power of 10, for example, from grams to kilograms, but occasionally you'll need to convert British units, or vice versa. For example, let's say you're given 1 meter equals 3.28084 feet. And you need to convert 8,611 meters to feet, which the answer is 28,251 feet. That height is quite close to Mount Everest, and I believe this image over here is K2, which is the second highest mountain in the world. Here's an example, the 8,000 meter peak. There are only 14 peaks whose summits are over 8,000 meters above sea level. They are the tallest peak in the world and are referred to as the 8,000ers. What is the elevation in feet of an elevation of 8,000 meters? And the only information you're given is that 1 inch equals 2.54 centimeters. To convert 8,000 to feet, we first need to convert meters to centimeters. So to do that, we take the ratio that 100 centimeters equals 1 meters, so that meters cancel out. And then the next step is that we need to convert centimeters to inches. And we're given this information here that 1 inch equals 2.54 centimeters. So now the centimeters cancel out, and then the last step is to convert inches to feet. So most Americans know that 1 foot equals 12 inches, so the inches cancel out, and we're left with our final answer of 26,247 feet. Here's a practice problem for you to do on your own. You have seen in a nice apartment whose floor area is 880 square feet. What is its area in square meters? The answer you should get is 82 meters square. Now you can find the steps, and if you look in your book, for example, 1.4. And here's one more practice problem for you to do. Where the posted speed limit is 55 miles per hour, what is the speed in meters per second and in kilometers per hour? And the answer you should get for A is 25 meters per second, and for B, 88 kilometers per hour. Again, the steps are shown in your book if you look for example 1-5. Alright, so that's it for this chapter. If you have any questions, please send me an email or swing by during enrichment. The next chapter that we'll cover will be motion in one dimension.